They come flowing out of my face. Yeah. We have blood sugars. And one of the girls we have, I was waiting for grandpa. So I got coffee with her and she was like, really? You're from here? Yeah. Really? Oh, you should. The application is really easy. We can work Starbucks and then. Really? Yeah, I did. But you have to like choose to send it without that's awful.
Its first test on the 20th or the 27th? It'll be on the 20th?
Should be on the 20th.
Okay, all right.
Yep. All right. So, picking up where we left off, talking about secondary structures. We talked Friday about primary structure and how it's just a long chain of amino acids. So now, secondary structures, we looked at our cis, our phi and psi angles, things like that. So there are two main types of secondary structures I'm going to want you to know about. The first of which is alpha helical structures, which is your most recognizable structure, the one that everyone is fairly familiar with. It is the right-handed turn, where we start at the bottom and it goes in a helical structure in a right-handed manner. Alpha helixes are characterized by two things. The first is the number of peptide units per helical turn. So that's saying if I start this amino acid, how many amino acids does it need to get till it's right above it? So one turn is from, in this case, here to here. So how many peptides did it take me to get around that? That's the first thing that characterizes it. And the second one is the pitch. The pitch is the distance the helix rises along its axis per turn. So that's this. This would be considered the pitch. So in this picture, I'm showing 3.6 residues per turn. So 3.6 is N. It has a pitch of 5.4 angstroms. So that would be P. So 3.6, they're saying this is 1, 2, 3, and a little bit to get to right on top of each other. 3.6 comes that way. There's 1, 2, 3, and almost 4 amino acids before you line up on top of each other, counting alpha carbon to alpha carbon. An alpha helix is also characterized by having favorable hydrogen bonding, and where phi and psi fall in favorable places on that Ramachandran diagram.
Can you move it over a little bit?
Sure. Also, alpha helices are very tightly packed. So in other words, looking at your polypeptide chain, this distance is pretty much right at the van der Waals allowed distance. They are as close together as they can get without becoming like an ionic or a covalent bond. They're as close as they can get and still interact. The R groups for the amino acids are going to be on the outside. So in this case, some of the R groups are here, there, there, there. So the R groups of amino acids in the alpha helix are on the outside of the helix. So if you're thinking of if that's the helix, the R groups are on the outer edges, either pointing out to the sides or front and back, however you are thinking about your helix. Why would I want the R groups on the outside? That's going to be where the chemistry's at. The R groups need to be on the outside because that's where the chemistry is happening with these R groups. So any amino acid can participate in an alpha helix except for proline. When we talked about proline the other day, what's the funny thing about proline? Chiral and? Right, it has its own ring. And so I'll draw it again over here just so everybody has the. Put it over here. All right, so proline's the one that makes a ring with itself, which means it's really hard for it to be in this kind of helix shape because the R group is really attaching to itself. If this is proline, it would really be making more like a circle like that, and it would throw off the alpha helix shape. So prolines cannot participate in alpha helix shapes. Can I flip it over and write some of my other notes on the back? Is that okay? Sorry. I have a few more fascinating facts about alpha helixes. So hydrogen bonding occurs between the first amino acid and the fourth, and then at fourth, and then eighth, and 8 and 12. So if you're looking at your picture back over here, this This is amino acid number 1, and it's going to interact with amino acid number 4. And I count a few more over. Keeps, yeah. Then the hydrogen bonding is going to occur between the carbonyl oxygen and amino group. So if I'm looking at those two different amino acids, one has the carbonyl group pointing up, and the other one has the amino group pointing down, and so the NH is going to interact with that CO that's been double bonded. That's where the hydrogen bonding is going to occur. So let's say we are starting our primary structure, and you got yourself 4 amino acids. How favorable is it to get those 4 amino acids to start curling on top of each other rather than just laying up flat? It is not very favorable, right? Because I have 4 amino acids. I have whatever my 4 amino acids are. And I'm trying to get this one to fold back over to interact with that one to start my alpha helix, right? Because an alpha helix has to start with that 4th one curling back around to interact with that 1st one. So that is not very favorable. But once I get my first 4 lined up, how easy is it then to get my next, to keep the chain going? Favorable, unfavorable? Favorable, unfavorable to keep the chain going? Favorable, yes. So would a long chain alpha helix be more likely to exist or a short chain? Long chains are more likely to exist. And by long, they are typically about 12 amino acids long. So 12 amino acids is the typical alpha helix length. Questions about about alpha helices? How they look? How they hydrogen bond? Okay, let's talk about some beta pleated sheets. All right, so these are repeating phi-psi angles that fall within the allowed zone of our Ramachandran diagram. And again, these are going to use hydrogen bonding, but instead of within the chain, it's hydrogen bonding between the chains. So hydrogen bonding, so beta pleated sheets, most importantly, have hydrogen bonding between 2 chains, not within itself. That's what sets them apart. I'll talk about these 2 types here in a second, but so beta sheets are aligned polypeptide chains. who have hydrogen bonding between two neighboring chains. So there are two ways we can make a beta pleated sheet with my two chains, not like the wrapper, that could be confusing. But beta pleated sheets though, I can make them either anti-parallel or I can make them parallel. And anti-parallel, one chain is going this way, where I have my nitrogen groups going, my amine end is now on the right, and my carboxyl group is on the left, my C terminus. C terminus is over here, my N terminus is over here. And this one has N terminus going to C terminus. So they're facing different directions. Any guesses on what happens in the parallel chain? They both go in the same direction. In this case, they've drawn them going this way. Okay, depending on how I line them up, the hydrogen bonds will line up differently. So in an anti-parallel configuration, the hydrogen bonds are lining up perpendicular to the chain. So here's my hydrogen bonding between my NH and my C double bond O. All right, so here's my NH, here's my C double bond O. Hydrogen bonding occurring between the two of them. In anti-parallel, that's not spelled right, but there we go. So in anti-parallel, we got our hydrogen bonds, and they'll be perpendicular to the chain. So right angle to each other. Right angle. In my parallel form, are my hydrogen bonds lined up parallel anymore? No, they're kind of at funky angles. I will eventually spell parallel right. So in my parallel configuration, the hydrogen bonds are not perpendicular to the chain. And so there's going to be different times when one is more likely to occur than the other. But based on just what you know about hydrogen bonding and lining things up, which of these two is going to be more favorable, structurally secure? Anti. So anti does occur more often because of the way it lines up. Those hydrogen bonds are nice and straight compared to the chain. So, when would a beta sheet form? And why do we call them pleated? Beta pleated sheets. It is. It looks crinkly. Does anyone have lampshades at home that have like that? That's a beta pleated sheet. It has like those, I don't know why those are trendy. And everyone knows what I'm doing when I do this. But yeah, lampshades, they have that. That's a beta pleated sheet. They have this kind of structure where it goes this way, then that way, then this way. They will often be pleated, just coming from the fact that they are trans, right? All of these single polypeptide chains, like a chain by itself, is in the trans conformation, so automatically, if it's trans, it's going to be in this form, right? Because I got that. All right, so each individual amino acid is trans compared to the one next to it, so they're going to be at alternating angles. Typically, why does a beta pleated sheet have to have at least one chain? Why does it have to start with two?
Bond together.
Otherwise, they can't bond together, right? It's not really a sheet if it's only one. I always have that question on my exam. What's the minimum number of strands required for a beta pleated sheet? It is 2. You'd be surprised how many people get that wrong. You need 2 to make a sheet. Write that down, star that somehow, because it'll be on the test. That's an automatic multiple choice answer. You need at least 2 strands to make a sheet. But you can have up to, typically 22 is the max. So 22 polypeptide chains lined up. And in terms of length, how many amino acids? They technically have 15 amino acids, top to bottom, in length. So what are some requirements for the beta sheet to form? What is our exception amino acid to everything we've talked about? Proline. Proline cannot make a beta pleated sheet. Proline causes trouble. We will use proline eventually, but just not for these kind of structures. Because again, proline would have the R group kind of make a ring over to this side, which would then throw off the trans conformation. We typically are going to use smaller amino acids, things like glycine, serine, alanine. Amino acids that do not have large R groups. They just have either a CH2 or just an H, things like that, so smaller ones. The other neat thing about these beta pleated sheets is that besides having 2 strands next to each other in this kind of conformation, they can also stack on top of each other. So I can have a beta pleated sheet here. That's really 2 chains right there. And then sitting on top of it in 3D space is another one. So if I have sheets stacking on top of each other, top to bottom like this, what does that do for that water? Will the water get trapped in there or get squished out? Get squished out. So what kind of R groups now can I use in my beta pleated sheets? I can use my hydrophobic ones as long as they are in the middle of a sheet. So unlike alpha helices don't use as many hydrophobic ones because the R groups are on the outside. And depending where the alpha helix is, the R group on the outside is going to probably be in contact with water. Beta pleated sheets can use these hydrophobic ones because when they stack, stacking eliminates water. All right, how we feel about these beta pleated sheets? Good. Questions about beta pleated sheets?
Is there amino M's? Oh, acids.
Acids, sorry, my A got kind of squished. Acids. All right, so then we have our third category of allowed secondary structure. which has the very generic title, Irregular Secondary Structures. So you have alpha helices, beta pleated sheets, and irregular structures. So just to clarify why these might be called irregular. So alpha helices and beta sheets are classified as regular structures. Because their component amino acids have a backbone configuration that are the same every time. So even if the amino acids change from one alpha helix to the other, all alpha helices are right-handed. They all stack up hydrogen bonds between 1 and 4 and 2 and 5 and whatnot. All beta sheets, regardless of which amino acids they contain, will either be parallel or anti-parallel, and they line up side by side and they stack on top of each other. Irregular secondary structures, which actually make up about half of all protein structure, are not random, but they are not regular. So two good examples are here and here. Okay, has anyone seen this kind of notation before? No. Okay. Helices in block diagrams are drawn as either spirals or, I think in your textbook, no, your textbook just uses them as spirals. That's good. Spirals in your textbook are alpha helices. Arrows that are flat like this are typically beta sheets. And what this diagram is saying is that I have two beta sheets that are lined up side by side, anti-parallel. But at some point, you gotta change direction, you gotta link them somehow. And so this is a hairpin turn that's linking two beta sheets. So I have my two beta sheets, these happen to be anti-parallel. Right, because one's going this way, one's going that way. They're lined up side by side, but you have to have some kind of linker between them. And so a hairpin turn is very common to link two beta sheets. What kind of beta sheets is this? Parallel, because they're going in the same direction. But now I have to connect this one to the start of that one. This is called an over-the-top loop. So in every protein structure, your secondary configurations, either your beta sheets, your alpha helices, have to be connected to the next secondary structure. And these are two very common ways to do it: hairpin turns or the top loops. And we'll look at some other examples of loops when we start looking at some actual proteins. But
So that's how they're connected through the...
yep, so I have amino acids going this way, and then I know I have another beta sheet over here, so to finish the protein, it just kind of makes a, I guess, over-the-top loop. Questions about my three types of things? Alphas, beta, yeah.
So they're just, are those any specific amino acids?
No, they can be just about anything. So proline could sneak in there if I wanted to. All right, that's the end of secondary, so let's take a look at tertiary structures. All right, tertiary structures and protein structure, especially looking at globular proteins, which, if I say globular protein, what picture are you thinking of? A big blob. Yes, that is correct. Big blob. So, globular proteins exist as a compact spheroidal molecule. Sphere-like, spheroidal. It's not exactly a sphere. Enzymes are typically globular proteins. I'll eventually get over this cold, I promise. So 3 common examples are enzymes, transport proteins, and receptor proteins. So if you've done anything in animal science or biology where like there's the proteins like on the cell that allows things to enter the cell or exit the cell, and they kind of are round-ish, ovally, those would be globular proteins. Why would my globular protein have a hydrophobic core? Where's the water in, compared to everything else? On the outside, right? So if this is my globular protein, right? I got my water over here. My amino acid on the inside is typically my hydrophobic amino acids. Which means, is my surface going to be hydrophobic, hydrophilic, or polar? It could be more than one thing. Mm-hmm. So hydrophilic and polar are good on the outside. Hydrophobic outside with polar amino acids, hydrophilic amino acids. So let's take a look at an example of a protein and how we kind of describe what's going on inside it. So this is an example of a 2-domain protein. Specifically, it's glyceraldehyde 3-phosphate dehydrogenase, which in about 2 weeks, you'll be able to tell me what this protein does based on just its name. We are not going to describe this. Anyone guess on what the action of this enzyme is? Dehydration. Excellent. You guys already got it. If it's a dehydrogenase, ACE means enzyme. Hydro means water. D means same thing it does in everything. Undo. So it's going to dehydrate the thing it's talking about. Glyceraldehyde 3-phosphate. Enzymes are named pretty obviously. So, well, next chapter is enzymes. We'll start talking about that. All right, so a domain let's see. I'll write over here. So a domain is a polypeptide segment that has folded into a single structural unit with a hydrophobic core. So in this case, this is a two-domain protein because there are two segments that have folded on top of each other to make a hydrophobic area. You can kind of see it. There's one up here, and there's one over here. It's all one protein, but there are two domains. And they are the domains are connected by one or two polypeptide segments. You can see that there's one connection here, and the other one is back here. There are two spots where it kind of starts over here, loops around, comes over here, loops around, and then comes back. And they've labeled the start and end. Here is the N, there's the C. So N, they're usually labeled N, C means amino acid 1. Then it loops, 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 goes up here, loops, 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 comes back down here, and ends with my C. And here's some of those things I was telling you about. So right here are some arrows, I mean beta sheets. Here's an alpha helix that's real easy to see. Then this would be one of those hairpin turns that flips around top of each other. There's some good hairpin turns over here. It connects the start to the end. Neighboring domains, meaning two domains that are next door to each other, obviously, are structurally independent, which means the way this one folded up did not affect the way that one folded up. Just if you're looking at its primary structure, it's just a long chain of amino acids, and this part folded up to get all the hydrophobics on the inside, and this one folded up to get all the hydrophobics on the inside. So neighboring domains are structurally independent units that have characteristics of small globular proteins. So it means each one, if I cut it in half, each one would look like a globular protein all by itself, and that it has the hydrophobics on the inside, hydrophilics on the outside, but they're connected to each other. And each domain usually has a specific function. Typically, that specific function is binding small molecules. So that's usually where the active enzyme site is within a domain, not between domains. Domains have a lot of secondary structure. Where I already pointed some out. They have a lot of alpha helices, beta-pleated sheets, over-the-top turns, hairpin turns. So they're going to be rich in secondary structure. Which means a lot of hydrogen bonding, I guess specifically internal hydrogen bonding, right? The alpha helices has a lot of hydrogen bonding within itself. Beta-pleated sheet, you can imagine there's hydrogen bonding going on over here and over there. So that's why it's a tertiary structure, because it's made up of secondary structure components. Okay, I'll do one last thing about globular proteins. So, stabilizing globular proteins. Folded globular proteins are only marginally more stable than unfolded globular proteins. Oh, yep. Sorry. So a folded protein is only about 40 kilojoules per mole more stable than an unfolded protein, which on the scale of delta G is pretty little. So of all the forces we've talked about, what is the most likely driving force to make a protein want to fold up? Hydrophobicity, yes. So the reason a protein wants to fold is not necessarily as delta G gets more negative, becomes more spontaneous. It's that those hydrophobic amino acids really, really, really want to get away from the water and would prefer to associate with themselves. So they are much more likely to fold inwards. And while hydrogen bonding is also important, it is not the driving force. Hydrogen bonding is not the driving force of folding. It's more like a fine-tuning adjustment to get the amino acids lined up better. So quickly, we'll do two. Two things that can help finish your folding. Can help stabilize, that's a good word. Besides our hydrophobic and hydrogen bonding. Our ion pairing between your polar amino acids. So above and beyond hydrogen bonding, hydrophobic effect. You still have your ion bonding, right? Your different amino acids will be charged. They can interact with each other. Looking at that protein we just had over here, our N and C terminus are going to be close to each other typically because one's positively charged, one's negatively charged. They tend to be close to each other in the final structure. And covalent bonding. In special cases, amino acids can covalently bond with each other. Does anyone know the amino acid that likes to bond to itself? Cysteine. This is typically. Cysteine can make a bond with another cysteine, a disulfide bridge. So we'll look at some examples of that coming up. But I know everybody's super excited to take this quiz.